Hello and welcome to Math 250. Our lesson is on section 6.2, orthogonal vectors. We say that a subset of Rn is an orthogonal set if every pair of distinct vectors in the set is orthogonal. This means that if we find the dot product of every pair of vectors in the set, we would get 0 every time. So if we have a set of 3 vectors, we would need to find the dot product of the first and the second, the first and the third, and the second and the third. So it's every possible pair. We would need to make sure that we got out 0 all the time. The subset is called an orthonormal set if the set is orthogonal and consists of entirely unit vectors. Those are vectors with a norm of 1. This means we can take our orthogonal set, find the norm of each vector, then divide each entry of each vector by its corresponding norm. We're going to take a look at 2 examples to determine whether or not each set is orthogonal. So let's say I have this first set of 3 vectors. I'll call them, for convenience, u, n, v, and w. If I find the dot product of u and v, I would get here 0, and then a 0 again, and then -1, and then 0 again. So right off the bat, that does not add up to 0. So I guess it's my lucky day. The first 2 I chose do not have a dot product of 0. So the answer here would be no, not orthogonal. However, if I go to the second group, let me call these u, v, and w as well. If I find the dot product here of u and v, that gives me 1 plus 1, and then I have -2 on the bottom. Those do add up to 0. So that's good, but we're not done. We also have to check the dot product of u and w. So if I go from u to w, I have 1. I have -1 from the second components, and then I have 0 from the last 2. So that's going to be 0 also. So I'm 2 for 2. The last thing I need to check is v with w. Just switch out the color. So that's 1 and 1 is 1. 1 and -1 is -1. And -1 and 0 is 0. So that gives me a grand total there of 0 also. So this, because I have all 3 pairs of dot product 0, the answer here would be yes. Meaning if I graph these out, the vectors will be perpendicular to one another. Here's a fun fact. So if we look back at our set of vectors that were and were not orthogonal, one of the things that we noticed is in the second set where they were orthogonal, these vectors are linearly independent. Meaning if we go back and make a matrix out of them and put it into the RREF, we will, we'll have 1 pivot in every column, all those equivalent properties we spoke of back in chapter 2. And there's a good reason why, and I wanted to just show it to you because I think it ties in nicely with some of the other proofs we've done this semester. So the theorem 6.5 states any orthogonal set of non-zero vectors is linearly independent. So it's sort of like an if-then statement. If I have an orthogonal set of non-zero vectors, then it is linearly independent. Linear independence doesn't imply orthogonality, but having an orthogonal set of non-zero vectors does imply the independence. And the proof is really cool. So you take an orthogonal subset of Rn consisting of k non-zero vectors. So before we had 3, but here we'd have k. And we have scalars c1 through ck such that c1v1, c2v2, all the way up to ckvk equals 0. Just like our proofs earlier on, we want to talk about the scalars and what that means in terms of the equation. So again, using the manipulating backwards approach, if I look at 0, that would be equal to the 0 vector times any vector vi. If I expand that out, because I have the orthogonality, I have the individual components, all those products, they all add up to 0 because the vectors we were assuming were orthogonal. So that means this whole thing is just the 0 vector, and I multiply that by vector vi, and then using our matrix vector properties and our dot product properties from earlier, we can just basically distribute this on the right. So I'm going to do a dot product on each of these on the right. So notice I'm just tacking on the vi on the right from section 6.1. And then, generally speaking, this is equal to ci times vi with the dot product there. And from theorems, I keep saying theorem, from section 6.1, vi times vi as a vector is equal to the norm of vi squared. But we went in saying that this was a set of non-zero vectors. So we can assume that the norm squared is not 0 because the vector itself isn't 0. So if the vector isn't 0, then it must be that the coefficient is 0. So that means, based on our definition of linear independence, if we have those 0 coefficients, then the set is linearly independent. So just a good proof to wrap your head around. If you want to take a look at it later on, compare it back to chapter 1, I think it would be a good thing to commit to memory. All right, so an orthogonal set that is also a basis for a subspace of Rn is called an orthogonal basis for the subspace. So we can just carry that concept of orthogonality over to bases as well. Likewise, a basis that is also an orthonormal set is called an orthonormal basis. For example, the standard basis for Rn is an orthonormal basis for Rn. So again, that just means 1, 0, 0, 1 for R2. That would be an orthonormal basis. If I find the dot product of these two vectors, I get out 0, and the norm of each vector is 1. So this would be considered an orthonormal basis for R2. I could extend it to R3 and R4 by adding in more components, more zeros and more ones. Similarly, I can take these vectors. I took this from your book, v1, v2, v3, as shown here. We can say that this is an orthogonal basis for the subspace that is the span of these three vectors. Remember, any span is a subspace. So we can show they are orthogonal, again, by calculating dot products of all the pairs. I can leave that to you if you'd like to do that. One of the nice things about orthogonality is we generally don't like fractions. So if we multiply everything by the same scalar, we can clear the fractions. So we would be allowed to multiply everything through by 4 to make this a little bit cleaner, and we would still have an orthogonal basis. After you have the orthogonal basis, then to make it an orthonormal basis, you simply find the norm of each vector and then divide each component by the norm. So for v1, the norm would be the square root of 1 squared plus 1 squared plus 1 squared plus 1 squared. And this ends up being the square root of 4, or just 2. So I would then turn around and divide all of these by 2. This is a nice compact way to write it. Or you can write half, 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 half. And same thing was done on these other two. I can find the norm and then divide each entry by that, by the norm. So then that gives me an orthonormal basis. So again, orthogonal means that we have the 0 dot products, but then orthonormal takes those orthogonal vectors and just divides each of them by the norm. Hence orthonormal. We can represent a vector in terms of an orthogonal or an orthonormal basis by using our work from section 6.1. We can take a vector u and v, and given an orthogonal basis, we can represent u as a sum or a combination, if you will, of the orthogonal basis vectors with coefficients we determine by using dot products and norms. So that's a nice little result there. Here's an example. I do have a longer problem to work through in a little bit, so I didn't want to overkill with the pen. This one is worked out already. So we have three vectors, v1, v2, and v3. And we would like to come up with a way to rewrite a given vector as a combination of the other vectors in the orthogonal basis. So first of all, if we take these three vectors, they do form an orthogonal subset. And if you want to verify this, you can find the dot product of any two. They should add up to 0 every single time. So we have that going. In addition, you can verify that these are linearly independent. If you want to also use the theorem that states if they're handing us an orthogonal set, they're automatically linearly independent. So then going back to chapter 4, we can say that the set of these three vectors form a basis. It is a linearly independent generating set. So now the question is there a way that we can rewrite the vector 3, 2, 1, this other different vector, as a combination, linear combination of the three vectors in the orthogonal basis? And we want to do this without any methods we previously learned back in chapter 1. We just want to use some of the work we've come up with in the vectors unit. So all we need to do is to calculate these coefficients, C1, C2, and C3, and each of them sort of weigh the amount of each vector in the orthogonal subset that we need to create the overall vector. So you simply do a dot product of u and v1 divided by the norm of v1 squared. That gives 10/14. So you weight it. You take 10/14 of v1. Same thing for v2 and v3. You calculate a similar coefficient. And if you weight each of those vectors, v1, v2, and v3 in those ways, the sum of all three of them will equal vector u. So it's another way to look at linear combinations, but just through a vector lens. And in your homework set, you'll have a chance to do this as well. The main part of this section answers the following questions. We like orthogonal bases. They're nice to work with. They have some nifty properties. But two questions naturally arise. Does every subspace of Rn have an orthogonal basis? And if it does, how is it found? What we're about to talk about not only provides a positive answer to the first question, but also gives a method for converting any linearly independent set into an orthogonal set with the same span. This method is called the Gram-Schmidt orthogonalization process. And this gives us a very, very important result. Every subspace of Rn has an orthogonal basis and hence an orthonormal basis. Remember, we get the orthonormal basis by dividing every component of each vector by the norm of the corresponding vector. So I'm going to be honest, the Gram-Schmidt process looks very intimidating. In its theorem form, it's a nice little computational exercise. Basically, given us a basis for a subspace W of Rn, you take your first vector in that subspace, U1, and we just call it V1. So we just leave it alone. Then we go to V2. We'd like this is the process of creating that orthonormal set. So V2, that we get by taking the second vector, U2, and then subtracting from it the multiple of V1 using the same coefficient process we talked about before. So we're going to find the dot product of U2 and V1, divide that by the norm of V1 squared times V1. So like I mentioned in the 6-1 video, this is not going to go away. We're going to see this whole, coefficient multiplied by a vector over and over and over again. Then for V3, we go into the set, we take our third vector, U3, out, and we subtract now two vectors. And each time we do a dot product with U3 and the previous vectors, and divide it by the norm squared, and then multiply it by the same vector. This just lists it out in general form. I think you can see the pattern as we go down. So if I had v4, I would then have u4 minus 3 different vectors there. And then if we take all the v's together, that creates an orthogonal set of non-zero vectors with the same span as the original set. And then we call that an orthogonal basis for W. Excuse the poor image quality, but I have this really great textbook that is a little old, and it shows the Gram-Schmidt orthogonalization process through a visual, which I thought was kind of cool. I couldn't find it online. I only was able to photocopy it and get it onto here this way. But basically, it just shows the whole process of trimming down, the vector a little bit. So that's where that whole division comes from. And then creating the orthogonal projection, and then, kind of rotating it so that we take this part here and just slide it over here. I guess translate's a better word, not rotate. And that's how we orthogonalize. So we're just going through this process of finding a projection, and we spoke about the projection aspect in the 6.1 video using this type of setup. So we find the projection, and then we subtract that off of the original vector, and we divide by the norm. So these three actions all together, we start out like this in figure 1, and we end up with this nice, neat orthogonal set here in figure 3. So if you want to take a look at it, I think it's a cool way to understand the meaning behind some of the formulas in this section, because the formulas can get a little cumbersome. All right, so we're going to use the long-awaited Gram-Schmidt process to find an orthogonal basis for this set of vectors. So if you'll notice, this actually is the same set we started with. I had asked if this set was orthogonal, and we quickly multiplied. I keep saying multiply. We quickly found the dot product of the first two vectors, and we found that it wasn't 0. So we said that no, this was not an orthogonal set. However, by using the Gram-Schmidt process, we can come up with an orthogonal basis for this set. So first of all, some things we can say about this set. The RREF of this set put together as a matrix would look something like this. So that tells us that our set is linearly independent because we have a pivot position in each entry, which is good. And also that it's not orthogonal right now. That's the whole purpose of using Gram-Schmidt. We will come up with a basis with the same span that is indeed orthogonal. So to go through the process, I just label these U1, U2, and U3 just to keep things simple. For our set, which I'll keep track of up here, I'll put our vectors as they happen up here. So our V1 by default is always our first vector. No work required. So I'll leave that there. That takes care of this step right here. Now I'm going to find V2. So for vector V2, I simply take vector U2, 0, 0, 1, 1, and I subtract from it the dot product of U2 and V1. So that will be 0, 0, 1, 1, dot 1, 1, negative 1, 0, over the norm of V1 squared. So that is the square root of 1 squared plus 1 squared plus negative 1 squared. That all gets squared out. And then we multiply that by vector V1, which is 1, 1, negative 1, 0. Some quick math to clear this up a little bit. I have here 0, 0, 1, 1. The dot product ends up just being negative 1 on the top, and on the bottom, the square of the norm is 3. And then I just recopy the v1 vector 1, 1, negative 1, 0. So this ends up being 0, 0, 1, 1 plus, I'm just going to distribute this in a third, negative third, and a 0. So for my final answer, my vector would be a third, 2/3, and 1. Some people prefer to leave it like that. Some prefer to factor out the fraction. That might be easier later on when you're dealing with dot products and whatnot. So if you'd like to factor out a third from each of these, you're welcome to do that. I will do that just to be consistent with your book. So I'll divide each of these by a third. A third by a third is 1. A third by a third is 1. 2/3 by a third is 2. And 1 divided by a third is 3. So I'm just writing it with a fraction outside. And this will be V2. Got my scarlet, black, and red colors here. Little Rutgers pride. All right, last vector is V3. So for V3, this is the heaviest lift. Vector V3 is equal to U3 minus the dot product of U3. It's so easy to make a mistake on these. U3 times 1, 1, negative 1, 0 over, I'm gonna save some space here. So the norm of V1 we already found was just 3, so I'm gonna leave that there, just to save a little time. And then V1 we said was 1, 1, negative 1, 0. And then the next one is the dot product of U3 and V2. So that's gonna get annoying. So for V2, I don't know if I want to use. I'm going to use the first version, a third, 2/3. You can use either one and 1. And then the norm of V2 squared is also a pain in the neck. So I'd have to write that out. So that's going to be a third squared is a ninth. Another third squared is a ninth. 2/3 squared is 4/9. Totally running out of room. And 3/3 squared, that's 1. 1 squared is still 1. And that gets multiplied by V2, which is the third, 2/3, and 1. Ugh, just made it. Okay. Lots of stuff going on there. So, so for V3, we are going to next just copy this down. 1, 2, 0, 1. We get a dot product of 3. I'm going to use a different color to point this out. So I got a dot product of 3 up here with a denominator of 3. So that's kind of lucky. My coefficient is just 1. And I can leave the vector 1, 1, negative 1, 0 alone. That'll happen over there. And then for this monster at the end, I have a third. 2/3 is 3/3, 0, and another 1. So that would be a total of 2 for that one. And then on the bottom, I have a big square root, a ninth, 4/9, and 1. We can make the 1 9/9 for a common denominator. So a ninth and a ninth, 2/9 plus 4/9, 6/9 plus 9/9 is 15/9. But then I'm squaring the square root, so that just leaves me with 15/9 by itself. And then I have here the third, 2/3, and 1. So at this point, maybe use a calculator. I don't want to bore you and run out of room with arithmetic steps, but you want to combine these all together and come up with your sum, which should be negative 2/5. You're going to see the 15 on the bottom will reduce down to a 5. So it'll be negative 2/5, 3/5, 1/5, and negative 1/5. And like I said before, you can go back up to the top and write that out with the fraction outside that sometimes is a little bit more desirable. And if I do that, I'm just stripping the bottom away and writing it as a fraction, and then just the numerators inside the vector. So that's 1/5, -2, 3, 1, -1. That is our v3. So these three vectors here are orthogonal, and you could check by finding the dot product of any two, and they have the same span as the original set of vectors do. That is the Gram-Schmidt process. I tortured you with a 4-component one. Luckily, the ones in the book are a little bit shorter, but I wanted to go through one that was a little more intense. And you're welcome to use a calculator to help with some of these more terrible calculations. Just keep your answers exact. All right, so the last part of the lesson is the QR factorization. So perhaps you've heard of QR codes. This is a little bit different. If a matrix with linearly independent column vectors A and Q is a matrix with orthonormal column vectors that results from using Gram-Schmidt process, what connection is there between A and Q? Is there some way to get from one to the other? So it turns out if A is linearly independent, is a matrix with linearly independent columns, and we have our matrix Q that has columns that form an orthonormal set in Rm, there is an upper triangular matrix R such that A equals QR. So once again, these triangular matrices come in clutch to help us rewrite matrices in other forms. So we call that a QR factorization of a matrix. So again, Q has orthonormal columns, and R is an upper triangular matrix. To find the QR factorization, we will go through a series of steps, and it turns out we can also use it to solve systems. To find the QR factorization, we're going to revisit our old friend. I didn't want to have us have to go through the painstaking process of Gram-Schmidt all over again. So we'll go back and use our friend matrix A. The good news is the matrix Q, we can take our vectors from the Gram-Schmidt process and just turn them into orthonormal vectors instead of orthogonal vectors only. So to get started on that process, let's go back over here. So to make matrix Q, I first have to go back and grab my orthogonal basis vectors from the Gram-Schmidt process and recopy them, but then divide each component in each vector by the norm of each vector. So over here, I'm just going to write down what those vectors were. So it was 1, 1, -1, 0. And the norm there is the square root of 3. That's 1 squared plus 1 squared plus -1 squared, all under the square root. The second one was a third, 2/3, and 1. If I add up the squares of each of those, I have a ninth, 4/9, and then 1. So that would be 6/9 plus 1. We can make 1 9/9. So 6/9 plus 9/9, that is 15/9. And if I take the square root of that, that is just radical 15 over 3. So we have to divide each term by that, which is the same thing as multiplying by 3 over radical 15. And then for the last vector, that one was -2/5, 3/5, 1/5, and -1/5. And for the norm of this vector, I would do square each of them. So it's 4/25, 9/25, so it's 13. Another 1/25, another 1/25. So that ends up being the square root of 15/25, which is radical 15 over 5. So like I said, each of these vectors now has to get divided by the norm in each column, and that creates matrix Q. So I simply take 1 divided by radical 3. There's our first entry. Same thing for the second, the third, and the fourth. So we'll see some repeats there. 0 divided by radical 3 is still 0. Next, the part where I have to divide 1/3 by radical 15/3, that can also be viewed as 1/3 times 3 over radical 15. When we divide by a fraction, it's better to multiply by the reciprocal. And if that's the case, we see the cancellation a little bit quicker. That's going to be 1 over radical 15. For the second term, same exact thing. For the third term, we just have a 2 on the top now, but same exact math. And then for the fourth term, 1 times 3 over radical 15 is still just 3 over radical 15. Last, in the third vector, for here we're dividing everything by radical 15 over 5. So we can instead multiply by 5 over radical 15. So for our first entry, we multiply instead by 5 over radical 15. So that gives us negative 2 over radical 15. And then likewise, going down the column, 3 over radical 15, 1 over radical 15, and negative 1 over radical 15. Your book uses the notation W1, W2, and W3 to stand for these orthonormal vectors here in the set that create matrix Q. So again, each of them has a norm of 1. They're orthogonal to one another, and that's half of the process. The final step is to create the upper triangular matrix R. Now, the good news is Q was a 4 by 3 matrix. For R, we go back to the definition of QR factorization. It says that Q is m by n, and then R is n by n. So R is going to be a square matrix, and its dimension matches the number of columns in Q. So Q is going to be, R is going to be a 3 by 3 matrix, again, because it matches the number of columns in Q. So the good news about that is because it's upper triangular, we already know that we have 3 zeros because we have the diagonal entries and everything else that we have to come up with. But there's going to be 3 zeros in the matrix before we even do anything. And to find the individual components of the matrix, we are going to multiply. Excuse me, once again, we are going to find the dot product of W1, W2, and W3 with each of the columns in the original matrix A. So we'll call these A1, A2, and A3. So for this entry right here, I'm just going to label, this is just my own kind of notation, just so I can keep track. The W's go this way, and the A's go this way. For this entry here, I am going to find the dot product of W1 and A1. So that means, for this spot right here, I'll just work this one out. I'm going to find the dot product of 1, 1, negative 1, 0 with 1 over radical 3, 1 over radical 3, negative 1 over radical 3, and 0. And when I do that, I get 1 over radical 3 plus another 1 over radical 3 plus another one. So that is 3 over radical 3 as my first entry. For the next entry here, I find the dot product of W1, again, this column, with the second column of A. So that's a little bit easier because I have 2 zeros in A2. So I get 2 zeros right away. Then I have negative 1 radical 3 by 1. And the last entry is a 0. So it speeds things up pretty nicely. Last, I'll do W1 by A3. So that is, again, this column here and then this column here, find the dot product there. So that is 1 over radical 3, 2 over radical 3. Those together add up to 3 over radical 3. So that's our third entry. And you just keep repeating the process. So then I would do W2 and A2, find their dot product. I'll just write that here. And then W2 and A3. And last, W3 and A3, that dot product goes here. And we can say now that our matrix A is equal to the product of Q, which has orthonormal columns, and matrix R, which is an upper triangular matrix that we arrived at from using columns of both A and Q. It's a nice little connection between the two. Almost done, I promise. This was a heavy section. So I guess the natural question is, why will we do this? So just like when we talked about LU decomposition, QR factorization also offers yet another way to solve a system of equations. And I know that Gaussian elimination, using the calculator, other methods are preferred, but this method has a nice advantage because it keeps things exact and it avoids a lot of round-off error when it comes to that. So suppose we are given the consistent system AX equals B, where A is n by n. If we have a QR factorization up front, we can use the fact that an orthogonal matrix transpose times itself is the identity matrix. This is a fact we will explore later on in section 6.5, but for now we'll just assume it as a fact. You can transform your equation AX equals B with QR x equals B just by substitution. We can multiply both sides on the left by Q transpose. That's allowed through matrix multiplication properties. Q transpose times Q is equal to the identity. Again, that's this little fact we're taking right now, but we'll talk about later. And then the identity by any matrix is the matrix itself. So we end up with this nice little fact here. And if you'll recall, when we solved systems with QR, having LU, when we solve systems with LU, having only one entry on the bottom is really nice for solving. When you augment on that vector at the end, you can solve for the last one and then backfill right up and find your solutions. So it offers a nice way to arrive at a solution to a system. What we're going to do is, just for the sake of not redoing a whole problem, I basically took our system from before and our matrix A from before, and I made a system out of it. So I did like 1x1 plus 1x3, 1x1 plus 2x3, negative x1 plus 1x2. I took it out of matrix form and just wrote it out as a system. And I made up a random solution here, B, of 2302. So if you would like to find the solution to this system, we can simply take our matrix R that we found before. That was 3 over radical 3, negative 1 over radical 3, 3 over radical 3 again, 5 over radical 15, 6 over radical 15, and 3 over radical 15. Right, that was super great. So if I use that as my R, and I have x1, x2, x3 as my unknowns, I then set that equal to the product of Q transpose times B. So over on the side, we just want to calculate what Q transpose times B is. So if I take our matrix Q and I transpose it, these rows each become columns. So I'm just going to rewrite that as a transpose. So now, again, rows turn into columns. Just recopying from the previous slide. All right, so there's our Q transpose. Next, we want to multiply this by matrix B. So then that gets multiplied by 23002. And then once we figure out what those are, we just join that right back up here. So that is a big row by column. That multiplies out, I'll save you the agony, 5 over radical 3. Same thing here, I'll do row by column. So that is 11 over radical 15. Same on the last, points in our matrix. Last row by column. If I do those together, I get 3 over radical 15. And then the advantages of using the QR factorization, that my last equation basically is 3 over radical 15 x3 equals 3 over radical 15. So that tells us that x3 is 1. Then in my second equation, I have 5 over radical 15 x2 plus 6 over radical 15. That's going to go with x3, but we found that x3 was 1. That equals 11 over radical 15. So you simply solve for x2. x2 will also equal 1 just by coincidence. And then last, you go back in and plug your 1s in up here. And we're looking to see what the value of x1 would be to give us out 5 over radical 3. And by coincidence, that also happens to be 1. Don't expect this to happen every time. But this is yet another way. We've learned a lot of methods in this course. And you can add this one to your list also. We can also solve systems by using QR factorization. And again, very useful when trying to avoid a round-off error that occurs, especially with these weird radicals that we got. All right, so I hope this was helpful. I'm sorry it was so long. I didn't want to skimp on any details, but this is everything that we need, and I hope that you found this useful, and I'll see you soon.